And Dawson is here. There are a few announcements. Our volleyball team, record-setting volleyball team, for some reason they have marks all over the board here. Okay. Today's the 25th. Just 3 shopping months left till Christmas. Volleyball team will be playing Gadsden State, unfortunately, in Gadsden today at 6 o'clock. So if you happen to be driving by Gadsden around 6, stop in and cheer them on to victory. And then the 30th, which is what day? Today's the 25th. That makes Friday the 27th. That will make Sunday the 20th. So sometime next week, they'll be playing Coastal Alabama South. We were playing Coastal Alabama East yesterday, so Coastal Alabama South will be next week on the 30th. This is interesting. Oh, I guess we have back-to-back matches. We're also playing Wallace State, Selma, on the 30th. Their match will follow the first one's at 4, the next is 7. Busy day. College Scholars Bowl is a team that's currently recruiting players with knowledge of any subject, including history, literature, science, music, current events, mythology, and mathematics. So if you would like to join that, Mr. Matthew West, whose office is right down the hall here, go down this half flight of stairs, head toward the end of the hall. When you pass room 259 on the left, then the next door is his office between 259 and 261. It doesn't have a number on it, but it has his name there. Check with him. He'll get with you on that. And coming up, the NASA Community College Aerospace Scholars Program is accepting applications for this year through October 16th. That's probably a little less than 3 weeks away, so get on top of it. It's a great program. I saw Dr. Wilson down the hall just as I was coming. She can give you a lot more information about it. There's several websites you can go to and find out more information as well. Okay. Any questions on anything that we've done so far? Let me get, I didn't get Kiara when she came in. All right, we got 5 people here. Yep. So, any questions? All right, let's go from current slide. All right, last time we were looking at center of mass for a planar lamina, and we did a problem or two with that. Whoever was in this class right before me must get in a hurry at the end and doesn't erase too well. Okay. And my work study student is going to try to clean the boards, but they were in here before she could get that done. All right. So the center of mass of a lamina of uniform density depends only on the shape of the lamina and not on its density, because it's uniform. The density will cancel out in the numerator and denominator when you're calculating center of mass. The density for the lamina will be a rho, and for the mass will be a rho, and they always cancel out. For this reason, the point x bar, y bar is sometimes called the center of mass of a region of the plane or the centroid of the region. Okay? Now, I'll sometimes mispronounce that because I have to take a drug called Synthroid. Okay? But this is not that drug. That's something for your thyroid. Okay? So this is Synthroid, not Synthroid. So if I mispronounce it, just understand Synthroid. In other words, to find the centroid, and that's spelled S-Y-N, by the way, to find the centroid of a region in a plane, you simply assume that the region has a constant density rho equal 1. And that way you don't even have to write it down. It's just 1. Compute the corresponding center of mass. Just like you had before, you just don't have any rows to carry around. All right. That then leads, here we go. 2 more examples before we get the theorem of Pappus. All right, I guess this is the best white space we're going to find. Let's do example 5. Well, let me get my pen set up. All right. Example 5. Find the centroid of the region bounded by the graphs of f of x. I'll put it up here. F of x is equal to 4 minus x squared. Okay. And g of x is equal to x plus 2. Okay. Find the centroid of the region bounded by those 2 graphs. Unfortunately, probably to get a good feel for it, we'll need to graph those 2. Okay? Cheat a little bit and look and see where my dimensions need to be. We know on the first one we're going up to 4. When x equals 0 will be 1, 2, 3, 4. And when x is either plus 2 or minus 2, we're at 0. Okay? So this is the parabola about like that. 1, 3, and minus 1, 3, and plus 1, 3. Beyond that. Okay. Now, x plus 2 has a y-intercept of 2 and a slope of 1. And I'm pretty sure that intersects right there. And also goes down here and intersects right there. So here is the line x plus 2. Okay. So it's going from the point minus 2, 0 to the point, and we're talking about this region here, 1, 3. Okay. So, our representative rectangle would be something like this, and okay, guess what, folks? No symmetry here that we can just say, oh, we know this one. No, we don't know either one. Okay? So we're going to have to do both the x bar and the y bar. Do you have a preference on which you do first? Or you may actually want to do the mass first, even though we're not really doing mass, we're just doing area, because density is 1. So what you want to do? You name it and claim it. Say again?
X bar.
X bar. So let's see what x bar is. X bar. Now, whoa, not that. Okay. For x bar, what we're going to have is the moment with respect to y, if you like to think of it that way. But let's kind of do it this way. What's your x bar for that rectangle right there? That's the moment from the y-axis, x bar. Well, that will be x, right? That gives you that. And then times the area. And what's the area of that? So this will be the integral x. And what's the area of that bar there? Anybody? How about the length of the bar there? Does Does that help? Okay. It's the difference of 4 minus x squared and subtract x plus 2. Now I'll write it like that, make it a little maybe easier to see, and the thickness is dx. With it there or not? All right with that? That's the numerator. Now what's your x going from and to? You're doing dx, so what's your limits on x? Say again?
We put a 2 outside the integral and then put 0 to 2.
Okay. The trouble is, it's not the whole parabola, it's just this shaded portion. That's not symmetric. Negative 2 to 1. Unfortunately, we got to do the whole shebang here. Okay? Now, what will your denominator be? Just the area. So that would be the integral from negative 2 to 1. Also, just without the x in it. So rather than write that whole mess down, let's go on and figure out what that is in the parentheses there. That's 4 minus a 2, so that's going to be 2 minus x squared minus x. Did I do that right? Okay. Dx. All right. Once we do that, we don't have to do it again for y bar. We'll just use what we get there. So since I've already done that here, since I'm running kind of short of room, let me do that here too. Okay. That was 2 minus x squared minus x. Okay. Now, in the numerator, we have to multiply through by x, right? So, can I just go on and do that as well without having to write everything again? So what I'm going to do is make this 2x minus x cubed, because it was x squared, minus x squared. And take out the x in front. I'll go on and lose the parentheses too. Okay. Now I think we can go straight to our integrals. The easy part, right? Maybe the parentheses would be good. I don't know. You tell me. Okay, what's the numerator? X squared minus. Got it? Okay, there's your numerator, evaluated from minus 2 to 1. Boo hiss. Okay, and your denominator is 2x okay, evaluated from minus 2 to 1. Loss of space here. Man, where can I go? What I think I'm going to do is erase our first two functions up here and see if I can write there. Is that all right? Maybe we're going to get rid of my dividing line here because it's just so cramped for space. All right, let's evaluate this one. Start with the 1. So 1 squared is 1 minus 1/4 minus 1/3 minus a negative 2 squared is 4, and then minus a minus is a plus, and a negative 2 to the 4th power would be a second. Yes, will be positive what? 16 over 4, which is 4 minus, all right, here's the other negative. Okay, good deal. We're in Chapter 7, Application of Integration, forever. 7.6, moments, centers of mass, and centroids. We're now in the centroid part, so we're near the end of it. Example 5 on page 500, top of the page. That's an ugly picture of it there. We're just evaluating this integral down here, okay? We just had done everything except the minus a minus, which is plus, but then negative 2 cubed is negative 8, so that's going to be a negative 8/3. Now that is not looking good, folks, because that comes out being a negative number, and that's not the case here. So what have I done wrong? All right, they keep on coming here. Josh is here, and Jemiah is here. So we're only missing Fred. Perfect attendance. Other than that, maybe he'll come in too. Okay, I've made a rather dumb error somewhere here. That looks the same. Oh no. Yeah, I'm sorry. This is X bar we're talking about. It is negative. Okay? Pretty obvious here that the X bar, since there's so little mass on this side, most of the mass is here, your X bar is going to be negative. Goodness gracious. Okay. What does it come out being? Okay, let's combine these two. Minus 1/3 and minus 8/3 would be minus 9/3, right? Which is 9/3 is minus 3. Okay. Now, except for that 1/4 in there, we're in pretty good shape. The minus 4 and plus 4 add to 0. That's sort of good. So you got a minus 3 1/4 plus 1. So that would be a minus 2 1/4. Okay? I say 1/4 and write 1/2. There's something wrong with the old gray cells here. Now that is not good. Well, doesn't seem good yet, because that's a rather negative. But we haven't divided by our mass yet, so let's see. Let's call that minus 9/4. You okay with that? That is your, I don't usually call it this, but that's your moment with respect to the y-axis. Okay? And that still doesn't feel very good there. But let's go on and see. Because it doesn't seem like it should be any further out than negative 2, because that's where we end here. But let's move on. Let's see. Just make sure I haven't done something stupid. X squared minus x to the 4th over 4 minus x cubed over 3. Yeah. All right. Okay. So we still got to do our denominator, and our denominator, let's evaluate up here. 2 times 1 is 2 minus 1/3 minus 1/2. Then we have a minus 4, which is plus 4. You see that? Minus because it's the lower one, but 2 times minus 2 is minus 4. So that's a plus 4 there. Then we have a minus, which is plus, but then you have a negative 2 cubed is, like you say, a minus 8/3. And then we have a minus, plus what? I can't hear. 2? Yeah. Okay, plus 2. All right, so let's see what we wind up with here. Again, these add to be a minus 9/2, which is 9/3, which is a minus 3, so I'll just write it over there. Here we have 4 plus 4 is 8, minus 3 is 5, minus 1/2 is 4 1/2, so that's minus 9/2. 4 1/2 minus 9/2. And if you take minus 9/4 and divide it by, whoa, that's not a minus, it's a plus, right? 4, 8, 5, oh, yeah, 5 minus 1/2 is 4 1/2. I think it is anyway. So that's 9/2, and divide this by 9/2, and you get negative 1/2. Yes! There is your X bar somewhere in that region. Now to do the Y bar. So let's just, and that's what they got for X bar. Good. All right. Now I'm going to erase a lot here to do my Y bar. Okay. I think I'll erase all this in here. And since we've already calculated the mass, just remember this up here, not really a mass, it's an area. This is our area. That's what they call it in the book, A. Okay, so let me erase that so we don't have to take up room with that anymore. Because that denominator is the same for both of these. And let's just get all of these out of the way. Gracious. My stomach is out here just rolling, saying, have you forgotten to feed me? And of course I didn't. It's not even close to lunchtime, but okay. So I'm just going to put my X bar over here. There we go. All right, let's do the Y bar. All we're going to do is that numerator for it. Okay, now what's your Y bar? Hint, the second part is exactly the same. That's the length of this times the width of it. Well, the length of that is your alpha of x minus g of x, which I wish I hadn't erased already. I've erased everything. So help remind me what that was. It was 2 minus x squared minus x. Wasn't that it? Okay. That's the second part of it. That's the height of this times the width is the dx. What's our the centroid, or the center of mass of this strip here? How do we do that? Remember from last time? Yeah, we weren't here last time. Remember what we used for the y part? The mean value, the average. So you take these two and add them and divide by 2. Remember? That's the middle, right there. That's the Y bar for that bar, okay? A couple of bars there. So remind me what my functions are. write them up here. F of x, I erased them from up here, is equal to 4 minus x squared, and g of x is equal to x plus 2. Okay? So we add those two together and take half of it. So I'm going to put the 1/2 outside. I know that's going to be there. And then we're going to add those two together, and we get 6 plus x minus x squared. Have I done that right? Adding those two together. Okay? Now that's a mess, isn't it? Okay? There was actually a little bit of an easier way to do this. And I want to investigate that now. Because what's in here isn't that, well, let's just go on and multiply them out. It's going to take too much time to do the other. Okay? So, oh, this is y bar. I left something off here. Now, this is all y bar. This is over the mass, or area. Area is what we're calling it. Okay? Area. All right. So that's going to be 1/2. Integral from -2 to 1. Okay? This is sort of a pain in the neck, but we can do it. Okay? Let's do the biggest term first, and that's going to be our x to the 4th. That would be x to the 4th. Now let's do the x cubed terms. Well, that would be this one times that one. So that's a minus x cubed. But then we have this one times that one. That's a plus x cubed. So those add to 0, right? See what I'm doing? Okay, let's do the x squared terms next. Okay, you got 3 of them. Don't forget them. This one times that one is, I'm going to write these out, minus 6x squared. This one times that one is going to be a minus x squared. And this one times that one is going to be a minus 2x squared. Does everybody see what we did there? Okay. Now our x terms. We're going to have 2 of those. This one times that one is a minus 6x. And this one times that one will be a plus 2x. And then the constant terms plus 12. And this is what we do times dx. All right. Now, this is all over a. Okay. So let's clean that up a little bit. Integral from -2 to 1. I'm just going to deal with the numerator for how 1/2 in front of that. Okay. X to the 4th. And here we have minus 9x squared, right? Minus 4x plus 12. Have I done it right? Y'all are supposed to be keeping track on me. Oops. All right. dx. Okay. I'm tragically running out of room again. So I'm going to go back and, well, let's see, where will I do it? I think I'll go back to this white space here and erase these again now that I've gotten them down again. I think I have them right. I don't think I'll need them anymore. I hope not. Okay, and let's do that integral. 1/2 times. It's the antiderivative of x to the 4th. Help me. Help me, folks. x to the fifth over 5 minus what's next? Anybody? Say again? 3x cubed. Perfect. Okay, it'd be 9x cubed over 3, which would be minus 3x cubed. Next. 2x squared. Next. Plus 12x. Evaluate that from minus 2 to 1. Okay. Now, I think, therefore I'm going to come up here and do some more erasing. If I can get it to erase. There we go. And rewrite the A is equal to 9 halves. A is equal to 9 halves. Okay. Now, then I'll erase this part to give me some more room to write over here. Okay. All right. So this is going to be 1/2. All right. When you plug in a 1, what do you get? 1/5 minus 3 minus 2 plus 12 minus what's 2 to the 5th? 32 fifths, but it's a minus 2 to the 5th, and that's an odd power, so it's going to be a minus, and the minus makes it a plus. 32 fifths. Okay? And then minus a minus is going to make it a plus. But then when you cube a negative 2, it goes back to being a negative again. So I think that's minus 24, isn't it? 2 cubed is 8 times 3 is 24. And you know those minus signs are listed there to trip you up. And you got a lot of them here. You have a minus there, but since you're doing the lower one, you're subtracting, but then you're cubing a negative number, that comes out negative. So that's bad news. Okay? Then we have a minus again, 2 times, but this time it's a plus 4, so that's going to be plus 8. Yay or nay? Not with me? And then finally we've got a minus. 12 times minus 2, so minus and minus is going to be plus 24. All right. Awful lot of numbers here, folks. Well, the good news is the minus 24 and plus 24 disappear. That's all right. We'll buy that. Okay? And the minus 2 and the plus 12 will be a 10. And 10 and 8 is 18. Minus 3 is 15. So 15 and a fifth. So we got 1/2 of 15 and 1/5. Now, I'm not sure if I'm doing my math right. Oh, I forgot this. Here we have 32 fifths. Sorry. Scratch that. I left off one. Okay. A very major one. So here we have a 1/5 and a 32 fifths. That makes it 33 fifths. Yuck. Could have done without that. So what do we have otherwise? We had 18 minus 3 was 15 plus 33 fifths. 33 fifths is 6 3/5. So 15 and 6 is 25 3/5. It doesn't get any better, does it? All right. Or we could do that as 15 is 75/5 plus 33/5. That would be second. It's 118, isn't it? Yeah, 100. You're right. 108 over 5. 108 over 5. Okay. Now, we're going to take half of it, so make that 54 over 5. 54 over 5 is going to be 10 4/5. Okay. Well, let's just leave 54 over 5. And then we're going to divide that by our mass, which was 9/2. So 54/5 times 2 over 9. Well, 9 will go into 54 6 times. So that'd be 12/5. Does that make sense? 12/5 is 1 2/5. So 1 2/5. 2 2/5. Sorry about that. 2 2/5 is somewhere right about here. Remember, it was -1/2. So that looks like the centroid right there. Does that seem reasonable? At least it's inside the space, so that's good. And you got as much down here as you have up there, it looks like. You have as much over here as you have over here, approximately. That's reasonable, okay? Let's see what they got 12/5 too. So our center of mass was your X bar was this is your Y bar. So the center of mass would be, or centroid would be -1/2 is your x-axis, x coordinate, 12/5. I say 12/5, all right, 15/5. I don't know what's wrong with the brain. Okay, 12/5. Okay. Yeah, and that's what they got to. Centroid of that region is -1/2, 12/5. Now, any questions on this? It's a mess, and I've erased so much, hopefully you've still been able to follow. Okay, so let's clear this and move on to example 6. Now, they tell us this. For simple plane regions, you may be able to find centroids without resorting to integration. Well, why is it in a calculus book then? Okay, let's see if we can figure out what we're talking about. It says, by superimposing a coordinate system on a region, as shown in the figure here, I wish they had shown this so I won't have to draw it. You can locate the centroids of 3 rectangles. Okay, so here is going to be the figure. Okay, it's supposed to be a straight line by definition. Okay. This is all approximate, okay? Okay. Wonderful looking figure there, okay? This is 1 unit here, 3 units here, 2 units here, no, 3 units here, 2 units here, 2 units here, and 6 units down here. Okay. Supposedly. My drawing's not very good. Okay. Spacings are not great. Okay. What they're saying is, by superimposing a coordinate system on a region, you can locate the centroids of the 3 rectangles. Okay? Now, they don't tell you which, well, they do. Okay. They say split it here and here. Okay? And that makes 3 rectangles. It's not the only way you could do it, but it's one. And the centroid here, as long as this is a laminar uniform density, would obviously be 1/2 is the x value and 3/2 is the y value, because that would be midway. That's the centroid of that thing. 1/2, 3/2. Okay, the centroid here. Now remember, if this is your origin here, and that's what they did, so this over here is 1 plus, okay. All right. 6 was the total length here. The total length here is 4. So you got 4, well, it's a length of 3 and a height of 1. So I know the y value is going to be a 1/2. Okay. The x value is going to be, this is 2, 3, 4. So that's going to be 3.5. So that's 7/2. Right? No, 5/2. Wait a minute. Yeah, 2.5. Yeah, 5/2. 1, 2. Yeah, my picture's ugly. Okay. 1, 2, 2.5. Yeah. 5/2, 1/2. And then this one over here is going to be there. That's going to be 5. And this is going to be 1. So 5, 1 is the centroid of that one. Okay. So what? Okay. Says using those 3 points, you can find the centroid of the entire region. First, you got to figure out the area. I mean, you always got to do an area. Okay. What is the area of this thing? The total area. This first block is a 3 by 1, so that's going to be 3. The next block's a 3 by 1, so that's going to be 3. And the last block's a 2 by 2, so that's going to be 4. So the total area is 10. Agreed? It's a 3 by 1 here, 3 this way, 1 that way. 3 by 1 this way, so that's going to be area of 3. And a 2 by 2 this way, that's an area of 4. Okay? Now, your x bar, you can treat that all the mass, everything else is located at those points. So basically your x bar would then be 1/2 plus 5/2 is 6/2, which is 3 plus 5 is 8. Over 10, which would be I'm sorry, wait a minute. I've left off something, sorry. Jumped the gun. Whoa! My pen eraser's not working. Okay, jumped the gun big time on that. Okay, your x bar, okay, it's not just it's the centroid, the center times the area. You have to include the area in it. Okay, got that. Because remember, it's this is representing that whole area. So the 1/2 times 3 plus 5/2 times 3 plus 5 times 4. That's what your numerator is. 1/2 times 3 plus 5/2 times 3, because it's representing that whole area, plus 5 times 4. And that's over 10. Okay? And your y bar would be 3/2 times 3 plus 1/2 times 3 plus 1 times 4 over 10. All right, let's see if we can figure out what those are. This is, I'm sorry? Because that's your total area. So it's the central, okay. It's x value times an area plus another x value times an area plus another x value times an area over an area. So that gives you your, in a sense, your average x bar. Okay, it's not really an average, but it's the centroid. Okay, you're doing the same here. Your y value times the area, y value times an area, y value times the area, divided by area, total area, and that gives you your y bar. Okay, so this will be, see if we can figure it out, 3/2 plus 15/2 plus 20 would be 60/2, right? Oh, let's leave it 20, okay? Because 3 plus 15 is 18, 18/2 is 9, so that'd be 29 over 10, which would be 2.9, okay? This one down here is 9/2 plus 3/2 plus 4. 9/2 and 3/2 is 12/2. That's 6 plus 4 is 10 over 10 is 1. Okay? So 2.9, that's almost to 3, and then 1. Right there is your center of mass of that thing. Now, does that seem reasonable? Okay? Well, you've got more area here than you have here. So yeah, this should weigh it this way a bit. Is that right? Seems like it would be. Yep, 2.91. That is it. I would have thought. Yeah, but this has more mass in a smaller x. This is more area in a smaller x. This is more area in a broader x. So that sort of balances out. So you're almost midway between 0 and 6, 2.9. And then because you have a lot more mass down here than you have up here, it's only 1. So yeah, looks pretty reasonable. And it is the right answer. All right. Any questions on that? Kind of we're going right back around to where we started almost, where you were doing it without calculus. Okay. So let's move on to any questions before we move on. Theorem of Pappus. Somewhere here. There we go. Here the theorem of Pappus says. And by the way, Pappus might be a good paper topic. I don't think I ever hear his name for anything else except for this theorem. But he must have been a pretty sharp mathematician. I think it's way back Greek, if I'm not mistaken. Let R be a region in a plane well, they're not showing R too well down here. and L be a line in the same plane. I see the L here, okay? Here's your R. This is it here. It's purplish on this side and reddish on this side. So, there's your R. I couldn't see it. There's your region, R, okay? And here's your line L, okay? In the same plane, okay? So this is the plane, and L is in that same plane, okay? Such that L does not intersect the interior of R at all, okay? So it's offset from where R is, okay? Shown in the figure. If little r, okay, is the distance between the centroid of R nope, wrong, okay. The region here is just the red part, just the red part. The blue in the background is the plane, okay. The blue in the background is the plane, just the red part is the centroid, is the R. And this is the line L also in that plane. So R is in the plane, L is in the plane. The blue is just the plane in the background, okay? Now, if little r is the distance between the centroid and that L, the perpendicular distance between the centroid and the line, then the volume that you get of the solid of revolution around that line L is 2 pi r. Think of that as the circumference that centroid travels as it goes around that line L, okay, times the area of that region, okay? It was a rectangular region, or it's shown here, but whatever region it is, if you can find the area of that region, the centroid of the region, and then 2 pi r times the, where r is that distance from the line to there, times the area of this, that gives you the volume of revolution, where A is the area of R. Note that 2 pi r is the distance traveled by the centroid as the region is revolved around the line, the circumference of that centroid as it goes all the way around. Okay. The theorem of Pappus can be used to find the volume of a torus or any other car. No, I'm sorry, this is spelled differently. As shown in the next example, a torus is a donut-shaped, don't say that while I'm hungry, donut-shaped solid formed by revolving a circular region around the line that lies in the same plane as that circle, but does not intersect the circle. Okay? So here's what we've got. Find the volume of this torus shown here, which is formed by revolving the circular region bounded by x minus 2 squared plus y squared is equal to 1. Okay, what does that tell you right there? What does this describe? I already told you it's a circular region, so it's a circle. Tell me something about the circle.
It's not discontinuous, but it obviously doesn't have a what do you call it?
Center of mass because of
Okay, yeah. Don't worry about the center of mass yet. Just tell me about that circle.
it's not at the origin.
Not at the origin. Where is it?
At 2.
X is at 2, but y is at 0. So the center of the mass is at the center of the circle. Too many centers of mass. Center of the circle is at 2, 0. Okay? And what else can you tell me about the circle? What does that tell you? Anybody?
Is a radius.
Radius of
1.
1. Not because that's a 1, because that's 1 squared. So x squared plus y squared equals r squared is what we're going with, because 1 squared is 1. That makes the radius 1. So you have a circle over here at 2, 0. So it's on the x-axis, okay? Radius 1, okay? And then your axis is over here, about the y-axis. So the y-axis doesn't intersect this because You're 2 units over here with a radius of 1, so you have some space there. You have a space of 1 here. So that, here it is. There's the circle. Center 2, 0, and it's 2 units from here. There's the y-axis. So you're going to take this circle and rotate it around the y-axis. Into the board, out of the board. Yeah. That. All right. Now, what's the volume of that torus then? What's the volume of the torus? Okay, it's going to be pi. Okay, 2 pi times r, which is 2, because the center of that circle is its centroid. We're assuming lamina, uniform density. So that's 2 pi times 2.
Times the area.
And what's the area of that circle?
2 pi, 2 squared.
Say that one more time.
2 pi, 2 squared.
Pi. Say again. Pi r squared. And what's the r? Now, okay, you got 2 r's here, folks. The r for the circle and the r for the revolution. What is the radius of the circle? You told me. 1. So that's just going to be pi, isn't it? Yeah, because 1 squared is 1. Okay? As we see right there. Okay? So what do we got? 4 pi squared. Whoa! Can that be true? Now, well, okay, I'll leave that a little bit longer. Just give me an idea of about what pi squared is. Just estimate it. About 10, because pi is 3.1416, and when you square 3, you get 9. Square a little bit more than 3, you're going to get something pretty close to 10. So this should be something pretty close to 40. Wouldn't you think? Let's see what answer they get. Oh, do y'all need this slide anymore? This slide? You got it? Okay. So let's see. The distance between the centroid and the axis is that. Yeah, we got it. Because the area of circular region is pi. Hey, sort of snuck that in. Then this would be volume is 2 pi r times a, but r is 2. So that'd be 2 times 2, 2 pi times 2 times pi, which is 4 pi squared, which is approximately 39.5. Yeah, that's pretty close to 40. Got it. Any questions? Need it longer? That's the last slide, and that's the last exercise in this section. We finally finished 7.6. Homework exercises here would be either 5 or 7. They're both at Calc Chat. 7's at Calc View. 9 should be at Calc Chat. 11 or 13, they're both at Calc Chat. 11's at Calc View. Any of the odds 15 to 27, they're all at Calc Chat. 15's at Calc View. 29, it should be at Calc Chat. Here's a couple of those you should be able to do without calculus type problems, and that's 31 and or 33. They're both at Calc Chat. 33's at Calc View. 35's at Calc Chat. 37 or 39, they're both at Calc Chat. 37's at Calc View. You can look into doing 41 or 43. They should both be at Calc Chat. 45 or 47 should both be at Calc Chat. No, I'm sorry. 45 to 49, they should all be at Calc Chat. Okay? 51 or 53, they should both be at Calc Chat. And then 55 should be at Calc Chat. And then 57 should be at Calc Chat. 59 is a Putnam challenge, which usually means they're really difficult. So only if you want to take a look at that. All right. Any questions in 7.6? All right. Let's discard that and go to 7.7. 7.7 is the last section in the chapter. So finally we're near finishing this, and what I'm going to do, I had meant to have my work study student take down the test to run off copies, but we got tied up in doing scheduling, and I ran out of time and didn't have a chance for her to do that before she had to go. So what we'll do, right at wherever we end here, I'll go down and make copies quickly for anyone who wants to work on it, have an extra weekend to work on the test. We won't finish 7.7, I don't think. It's a fairly short section, but we might. So let's go with it and see what happens. We're still in Chapter 7, Applications of Integration. 7.7 is fluid pressure and fluid force. The objective there is to find the fluid pressure and the fluid force. That's pretty straightforward, isn't it? So let's talk a little bit terminology here. This math author is pretty good at bringing physics into things. Pressure is defined as force per unit area over the surface of a body. Now, I don't know if you find that something easy to remember. I do now because I've taught it long enough. But originally, I thought of it this way. What is a unit, a typical unit we use to measure pressure? What is something we usually measure pressures of? I'm thinking you guys, probably more than you gals, maybe you gals as well. The tire pressure. And what do we usually measure that in? PSI. What does PSI stand for?
Pressure square inch.
Pounds per square inch, exactly. Well, what is a pound per square inch? A pound's a force, a square inch is an area. So that's how I remember pressure is force per unit area by the unit, pound per square inch, force per unit area. Okay? In general, the pressure is proportional to the depth of the object in the fluid. Okay, this is getting to, well, it's going to be related to Archimedes' principle, but we'll get that later. So here's the definition of fluid pressure. The pressure P on an object at a depth H in a liquid is P is equal to the weight density of the liquid. That's weight per unit volume. Okay? That's weight density, weight per unit volume, times H. H is the depth. Well, so weight per unit volume multiplied by a linear dimension, depth, that wipes out one of the, a volume is a cubic length, right? Cubic meters, cubic feet, cubic yards, whatever, cubic inches, whatever. And then if your H is also a length, be sure it's the same length, that would cancel one of those out, and you would wind up with weight per unit area, which is a pressure. WH is a pressure. Weight per unit density. Weight density, which is weight per unit volume, times H is a weight per unit area. Okay? And I can't believe they're taking a slide to do this. Below are some of the common weight densities of fluids in pounds per cubic foot. Okay? Ethyl alcohol, 49.4, gasoline, 41 to 43. So alcohol is a little denser than gas, but not by much. Glycerin, far denser. Kerosene, a little bit more so than ethyl alcohol. Mercury, goodness gracious, that's a different order of magnitude there. Densest liquid known, that commonly known, okay? And seawater, 64. Fresh water, or purified water, 62.4. This is because you have salts dissolved in fresh water, and that gives it a greater density. Okay. Now, what's the ramification of this? That seawater is denser than fresh water.
Salt and stuff.
Okay, yeah, that's why. What's a practical ramification of it? Have you ever swum at the beach in salt water? You float more easily because it's a denser medium. In fresh water, you aren't going to float as high. Salt water, you'll float a little bit higher. I don't know if you've noticed on boats that go into freshwater areas like rivers and lakes, but also go into saltwater areas, they have two lines that indicate where their water line is. For fresh water, it'll be up here, and for salt water, it'll be down here. So they float higher in the water. You'll see two of those. Okay. And this also indicates kerosene, gasoline, ethyl alcohol float on water because they're less dense. Glycerin would sink in water. And mercury, lead would float in mercury, and does float in mercury because mercury is that dense. They don't give the density for lead, but it's there. Now, they have a little blurb on the left. Blaise Pascal, known for his work in many areas of math and physics, and also for his influence on Leibniz. Okay? Though much of Pascal's work in calculus was intuitive and lacked the rigor of modern mathematics, he nevertheless anticipated many important results. Now you might say, so what? Why did they bring him up here? I'll tell you in a minute, okay? But let me first say this. When it says, although much of his work in calculus was intuitive and lacked the rigor of modern mathematics, if I'm not mistaken, I may be wrong on this, Pascal and it seems like maybe Descartes and a few others of those characters, Fermat, I believe, they were also, because they were really good at math, they were pretty good at gambling. And they figured out statistics. They were the ones that did a lot of the early development of statistics just so they could cheat at gambling. I mean, have an advantage in gambling. It took Florence Nightingale to come along and apply statistics to something very practical like disease prevention, cleanliness, doing the right things in hospital. She showed the doctors, look, she showed them the statistics. If you do this, this will happen. So she was the first applied statistician who did it for something other than gambling. Okay, so anyway, I always remember Pascal by that. I may be wrong. Another thing that he's famous for is Pascal's triangle. Y'all know what that is? It's how you expand the binomial. It's the coefficients you use. 1, 1 and 1, 1, 2, 1, 1, 3. 1, 3, 4. Wait, I can't do it. But anyway, it's that triangle. You have ones on the outside, and then your interior are the sums of the two above it. You expand the binomial that way. Okay. Was all over mathematics. Why is he mentioned here? Well, he did some of the early work in this kind of stuff too. In fact, when calculating fluid pressure, you can use an important and rather surprising physical law called Pascal's principle, named after him, Blaise Pascal. His principle states that the pressure exerted by a fluid at a depth h is transmitted equally in all directions. Okay? And we'll see the picture of this coming up later. Because of his work here, they named the SI unit of pressure. Pressure here we're talking about pounds per cubic foot. No, pounds per square foot. Okay? Pounds per square inch. That's the U.S. customary. In the SI unit, they don't use weight density, they use mass density. So it comes out kilograms per cubic meter, per square meter. Sorry, I'm saying it wrong. Per square meter. And what is a kilogram per square meter? A Pascal. Okay. They named the unit after him. Now, so on your tires these days, if you're looking to see what the pressure should be, you might find PSI, but either that will be in parentheses or another number will be next to it. And what's that other number? What unit? A kPa, meaning kilopascal, named after Blaise Pascal. Check your tires. They may not even list PSI anymore, but they're all, now modern tires, all have the kPa. Some of them may have in parentheses what the PSI reading is too, because the whole world uses Pascal, we don't. Now, by the way, a Pascal is a very, very small unit of pressure, because, see, a kilogram, whatever mass that is, not that big. I hope I'm saying this right. It may be a Newton, but it's pretty small, okay? But a square meter is huge. Look at a doorknob there. The area of the door underneath by the doorknob down, that's about a square meter. But that's a huge area for a fairly small either mass or force, okay? So therefore, a Pascal is an incredibly tiny thing. If someone were to, is the door open or closed? Okay. If you were to close the door, you're going to increase the pressure in the room by several pascals. Did you notice that? No. Okay, so to measure pressure, kilopascals, thousands of pascals. So anyway, let's move on. So here we have, when calculating fluid pressure, you can use an important physical law called Pascal's principle, named after the French mathematician Blaise Pascal. Pascal principle states that the pressure exerted on a fluid at a depth h is transmitted equally in all directions. For example, in this figure here, if the pressure at the indicated depth is the same for all three objects, okay? If the object is laying flat here, the pressure is 1. If it's vertical, well, part of the mass is up here, part of it's down here. Pressure at this point is the same for this one, that one, and this one. At an angle, it's still the same. At that point right there, the pressure is the same. Pressure at H is the same for all three objects. Okay. Now, because the fluid pressure is given in terms of force per unit area, that's what pressure always is. So it would be newtons per square meter. I was saying it wrong. Newton per square meter is a Pascal. P is equal to F divided by A, force divided by area. The fluid force on a submerged horizontal surface of area A is F is equal to P times A. Because multiply both sides by A, and you get the force. Okay? So F is equal to P times A. Force per unit area times area is force. Pressure times area is force. All right. Here's example 1. Flip the page. Page 506. Find the fluid force on a rectangular metal sheet measuring 3 feet by 4 feet that is submerged in 6 feet of water, shown here. Horizontally submerged. Okay? The fluid force on that metal sheet. So what you need to know? You need to know the pressure, and you need to know the area. Okay. What's the pressure? Pressure is weight density times depth. Okay? So let's put these things together. Okay. Let me get my pen back. Okay. pressure is equal to weight density times depth. Okay? Also, what are they asking for? Fluid force. The fluid force is equal to the pressure times the area. Okay? Force per unit area times area, that gives you force. So, it's in water. We're going to assume that's fresh water. Does anyone remember what the density of fresh water is? The weight density? 62.4. 6. Which did you say? 62.4. Okay. So the W is equal to 62.4. What units? Cubic feet. Right. Okay. Back here you'll see weight density in pounds per cubic foot, 62.4. Okay. What's the depth? 6 feet. Okay. So the pressure would be again? Yeah, and that would be 374.4, right? I did it in my head, I may be wrong. Anybody got it? Is that right? Okay. What units? Pound per square foot, because this foot cancels one of those out, leaving you square feet. Didn't know you had square feet, did you? Okay. Then, the force is that pressure, 374.4 pounds per square foot, times, what's the area of your sheet? 12 square feet. Oops, I put cubic feet. I said square and put cubic. Those cancel out, and somebody with a calculator, I'm not going to do that one in my head. 374.4 times 12. Anybody? You say 1,000? 4,000, that's what I thought. Okay, 4,000 what?
1,492.8.
And that would be pounds. Okay? That would be the force of water on that sheet. Okay? Now, I'm afraid I don't know how the book did this, but his physics is okay so far, but not with significant units. Because he only gave you one significant unit there, one significant unit there, one significant unit there. So if you're doing this physically, dimensionally correct, you say about 4,000 pounds. Because you really don't have the precision in any of your measurements to give 5 decimal places of precision. Now, I have a feeling they give all 5. 4,492.8 pounds. No way you can get that much precision out of the numbers they gave you. Now, even the weight density had no more than 3 digits. So if you figured everything else was exact, then you could at most say 4,490 pounds. If that was your limiting factor. If everything else was absolutely exact, then you still couldn't get but 3 digits out. But that's a different issue. All right. Now, let's see how they did it. The pressure is 62.4 times 6. That's the weight density times the depth. 374.4 pounds per square foot. Multiply that by 12 square feet, and you get 4,492.8 pounds. Result is independent of the size of the body of water or anything else like that. The fluid force would be the same in a swimming pool, a lake, anything that was bigger than 12 square feet with the proper dimensions, okay? So, that leads to definition of force extended by a fluid. Basically saying what we've just done. The force F exerted by a fluid on a constant weight density, W, per unit volume, weight per unit volume, against a submerged vertical plane. Okay, going to something different here. From y is equal to c to y is equal to d is this. Boy, they just jumped right into this, didn't they? The force is equal to the weight density. Now what you have to do now, rather than h, you have to integrate your h, okay? Now what you have here, the h is a function of y, okay? That's the depth of the fluid at any point y. And L sub y is the horizontal length of that region y. So basically what you've got here, and you also have a delta y here. So if you look at this, this is a depth, a length, and a length. And the depth is also a length. Okay? And this is force per unit volume. Well, there's a length, and a length. Those three multiply out, dividing into your volume here, and that gives you a force. So that sort of makes sense. What your problem becomes then is getting your depth as a function of y sub I, and your horizontal length as a function of y sub I, and then the thickness, delta y, that takes up your other dimension. So I wish they had the picture here. This is an object whose, I think it's the top edge is at C and the bottom edge is at D. I believe that's how they measure this. Let me see if they'll come. Ah, here's the picture. Okay. I wish they had shown this picture that's in your text. Did I skip over it? Nope. Didn't skip it. If you look at the picture in your text, okay, looking at this again. Wait. Yeah. They put C at the bottom and D at the top. And, okay. I had to see how they were naming this. They put the x-axis at the top of the container. So D is at the top of the thing submerged in it, and that's a negative number. And C is a more negative number. So you're integrating from the lower number, a very negative number, to a less negative number. So that's why they're doing this. I wanted to see if they're counting y positive downward, then it would be top to bottom. But they're doing y. So this is correct. Just, I wish they'd have shown the picture first.
Oh no, that's the weight.
The L you might think of as a width. The H is the depth, L is the width of that at that depth, and then dy is the thickness. So
That's volume type thing? You said depth.
it comes out with a volume unit. You're not talking about a volume of water because the H it's a measure that's measured in length, but it's not measuring a volume of water. All right, so here's example 2. I think we may be able to get this. A vertical gate in a dam has the shape of an isosceles trapezoid. Now, what does an isosceles trapezoid mean? Two sides are equal, and those are the two lateral sides. These two sides are equal. Iso means same sides, okay? Isosceles, two sides are equal, okay? Trapezoid that's 8 feet across at the top, 6 feet across at the bottom, height of 5 feet. So it says, what is the fluid force on the gate when the top of the gate is 4 feet below the surface of the water. Okay. Lots of measurements there. Okay. Now, remember, force is equal to the density, weight density, and as far as we know, this is fresh water, so we know that, times the integral from C to D, and that's the bottom. So here you're 4 feet down, here you're 5 more feet down, so you're going from -9 to -4. Okay? Yeah. Okay? Now, you have your H as a function of Y. You have your L as a function of Y. And then you have your dy. Okay. Now, your height, H, is the depth of the water as a function of Y. Okay. Well, at the top here, it's going to be 4 feet down, and at the bottom, it's going to be 9 feet down. So, okay. The depth you are at any time, see, draw your little dy in here. Okay. Now, what is the y value there? Okay. Your y is this depth here from surface of the water, not from top of the dam. I assume they're going to do surface of the water, not top of the dam. Let's see. Where are they measuring from? Looks like they put it at the top of the dam. So they put top of the water. I think that's where they put their coordinate system. You have to know where you're talking about here. This is your y-axis and your x-axis. They split down the middle here, and I believe they put it there. So your this is your depth that you are here, and you're going from I think your limits are going to take care of it. So I think y will do it for you right there. I think that's all you have to do. Your h of y is minus y. Now, why minus y? Because all your these y's are negative here, and your depth is a positive number. Okay. Otherwise, you'd come up with a negative force. So your h of y is equal to minus y. And that's what they say in the book. That's why I had to look to begin with to make sure they didn't have depth of water y increasing going downward. If they did, that makes this a lot easier. Okay, but now we have to figure L as a function of y. Okay? So your L at minus 4 is going to be 8, and L at minus 9 is going to be 6. So basically you have and this is your y value here. No. Yeah, and this is your length here. So length is a function of y. So you could say, and you can put it either order you want to. I think it works better here. 8 minus 6 is to minus 4 minus 9. So that would be 2 over 5. Okay, so you're losing 2 feet. Okay. They're going to do it slightly differently from that, which probably is a better way to do it. And in fact, we're out of time. Let's wait and do this. I thought this was going to be a little bit more direct than what it is. Let's wait and do this one next time. So we'll pick up and start back with example 2 next time, because I wanted to go get copies made for you first. Homework exercises here. I think you can do either 3 or 5, both at Calc Chat. 3's at Calc View. 7's at Calc Chat. And you can start working on 9 through 13 if you want to. We haven't quite gotten far enough to do that. Well, you might be able to, but all 3 are at Calc Chat, 13's at Calc View. You can stop there. Let me get your test run off. Okay. Sorry, I should have, like I said, already had this done. Okay, this is chapter 7. Now, if you want to go, you can. If you need to go, you can. You can come back and see me sometime when I have these done. Goodness gracious, I can't find it. I've started from so many different places, and here it is, I think. Nope, that's chapter 5. Chapter 7. Where is it? There we are. I think I found it here.
Can I get it from you tomorrow?
Yeah, that'll be fine. Yeah. Okay. Area. Volume. Yeah. Okay. Make sure that's the same one. Yeah. I don't want to give you one and have a different key. All right. I think we're down to 9 people in the class. I'll run like 9 copies fairly as quickly as I can. Right back. Sorry that took longer than I intended.